EC 111, UCSD, Lecture 8, Verilog examples for finite state machine in test benches. Writing a finite state machine is actually an experimental practice. There is no one best way to do it, but there are ways to do it better, or better design practices which we recommend, so it makes your design easier and makes debugging it much easier. The first step in doing that, of course, is to just understand the problem and compose a finite state machine that corresponds to that problem. And this is again an area where we can just do it if we have the experimental means, if we have done it before, we understand how this works, and then we kind of go ahead and do it. So that's what I'm going to do today in this lecture. I'm going to go through examples of finite state machine, how we form the state transition diagram for a finite state machine. And once we form the state transition diagram, we're going to talk about templates that can translate that diagram into a format in Verilog that is understandable. Again, this is not a unified format. You could do many different ways to express it. This is just to give you guidelines and make your design easier and nicer to compile and review. Now, the first example is a vending machine. The set one is going to talk about the design of the finite state machine for a vending machine. And as you know, a vending machine is nothing else that accepts coins and then disposes the items that we want to buy. In this particular example, we have a drink dispenser, and the inputs that are acceptable to this are 5 cents or nickel, dime, 10 cents, and a quarter, 25 cents. And then once we reach a 35-cent limit, it's going to dispense a drink. And then it also returns change. For example, if you're entering, to 25 cents, it will be 50 cents, and then it has to give us a change of 15 cents before the transaction is complete. Now, how do we start? There is no unique way to do this, but let's start by thinking that the vending machine has just sold something. It's in a reset state. There is nothing in the machine, or there is no money in the machine. So we start always from a state of S naught. And in this particular example, S naught is pretty clear. It's the first state of the problem. And it is the state where, we have an equivalent of a $0 in the machine. So, before we go to this state diagram, maybe it helps to think about this vending machine in a higher level format. So, we think of the vending machine as a input, as a box with inputs and output, and the inputs are clearly the money that we put in this particular case. We put the nickel, dime, and quarter in to the vending machine module, and then what does the vending machine does? If it is it's going to do some computation. If it reaches 35 cents, it's going to dispense a drink. If when it's dispensing a drink, we may have a change. It could be a nickel out or a dime out or both. Basically, there's a change dispensing module that dispenses the change. Now, the finite state machine is going to take care of this abstract machine that we just described. Now, imagine that we are in that state. First of all, as I mentioned, there are many different ways to express this finite state machine. There is no one way to do it, but there are many possible ways to pay for the drink. And here are some examples of that. But we are always, no matter what, we are always going to start from scratch, from zero. And then depending on how much money you have in the machine, the next state is going to be determined by what kind of input you get. For example, doesn't matter if I have a 10 cent because I got 10 cents in one, in one 10 cents, or I got 2 nickel. And, if I'm in the 10 cent state, that is, what matters. So, I guess, you know, when you start from like that $0 state or the reset state, then, you know, the next state is naturally the lowest amount of money you could get, which is, you know, 5 cents. And then, you know, from that 5 cents, you know, you could get another 5 cents and go to the 10 cents. And then, or you could go directly at 10 cents and go to that 10-cent state. It really kind of doesn't matter, but you know, this start, as I mentioned, is a $0. Now, you know, if I, you know, get the 1 nickel, if I get like the input nickel, I'm going to go to the 5 cents, and then, you know, I would, if I get another one, I go to the next one, and if I get like from the start at 10 cents, I'm going to go here, right? Then, you know, it's kind of a straightforward practice to do this this chart. So the most simplest cases, I just get 5 cents, 5 cents, and I go through each and every state that I have here. But you know, there could be other ins, for example, a dime in, and if I get the nickel in, I would go this way. If I get a dime in, I go from 0 to 10, from 10 to 20, from 20 to 30, or I get it here, I go from 5 to 15, from 15 to 25, and you know, that's the way I would transition in. And now I add a quarter. So if I get, like, if I have 5 cents and I get a quarter, I go to 30 cents. If I have 25 cents, if I get a quarter in, I directly go to the 25 cents, and so on and so forth. But there is actually, like, as you could imagine, there is a state missing here, and that is because, you know, I need to also dispense. So you know, of course, you know, we look into what happens, you know, when you get to 25 cents and you get a dime in. That means that, you know, I'm going to go to the idle state and I'm going to dispense. So here, you know, this 100 is a dispense, but, you know, there are other ways I could dispense. So I could get a if I'm at the 30 cents, I get a nickel. That means that I get a 35 cents. I go back to the idle state, and I also flag my output as dispense. So it's going to dispense a drink. Now, how do I explain to this the dime? Because, you know, if I'm 30 cents, I get a dime in, I have to dispense, but I also have to give 5 cents back. So, you know, there are many ways to express this in this particular example. This is a milling machine. How they do it is they define a different output state, which dispenses and also outputs a 5 cents. The same is true here. Like if I'm 25 cents and I get a quarter in, I'm going to dispense a drink, but I'm also going to dispense 15 cents out. And so on and so forth. So this way, you know, I'm trying to design this, but what happens if I'm in 30 cents and I get a quarter? So, you know, in this particular scenario, I have to give out 2 10 cents, which I don't have because, you know, these zeros and ones here, they give me the number of 10 and 5 cents that I'm dispensing. And if I'm dispensing 2 10s, I don't have a state for that. So, you know, there are many ways, again, to do that. One possible way would be to increase the number of output bits. Another possible way would be to add 1 state, which is, you know, what is happening here. So, you know, in this particular example, if we get a quarter in after 30, this would be 55. And then because 55 is, you know, we need to dispense 2, we have a state which is minus 10, which dispenses 1 dime. And then we have another kind of regular state and dispenses the drink. And then there's another state which kind of dispenses the other dime. So we dispense 20 cents and then we get the drink out. Now, you know, no matter how you decide to wire this finite state machine, there is no unique way to do it. There are kind of standard, I wouldn't call it even standard, but like known practices for doing that. And to me, like teaching this logic design and Verilog FPGA course for many, many years, I have seen people doing it in so many different ways. There's really not a unified solution, but what happens here is that once you have that, we have a recommended practice how you are going to translate this finite state machine, which is in the form of what we call a state transition graph. How do we translate it into a Verilog program which is readable and which can be debugged later? And again, this is just a practice, not something that you really need to follow. You could design things differently and still have a good functionality, but this makes it very clear. And again, if I'm defining a module here, what I do in this module vending machine, I go back to this figure, and I see, you know, what happened with this module. And what happened with this module is that I have the inputs to this module, I have the outputs from this module. And I'm going to exactly the same thing for this interface here. I'm going to talk about, you know, of course, the clock and reset are there for all finite state machine, but because we have the reset state and the clock, which synchronizes all activities, the inputs are as we had in that diagram, input-output diagram. The output register is a dispense, which dispenses a drink, and the output registers dime out and nickel out are also other states for the output. Now that we have the interface for this module, which is defining the high level of this module, what we are going to do is we are going to have the parameters. In this particular case, you know, we just, for the readability, we are going to define some local parameters, and you know, these are basically the states. So we have the states that we had in that other diagram. We had the idle 5, 10, 15, 20, 25, 30. And remember, like the O10 state that we added to come across the 30 plus 25 problem. And, you know, the states, if you remember, we had this states which were three bits here. And we are going to have variables that define this present state and the next state. And this is the interface to the module. Now that we have the interface to the module, we are going to define like that state transition diagram. So now we are going to do the combinational part of the circuit, which is going to say when we have you know some state and we get the input, what happens combinationally that we transition to the next state. And the way to do this is to just have the always combinational statement. It actually should be, I think, a lowercase a. But you know, what happens is that, you know, we're going to say, you know, in inactive values for the output, and then for the case, we're going to say what happens, you know, in the first state, which is basically the idle state, and then when the input comes, how do we transition from one of these to the other. State transition diagram into text, as we see here. Now we continue until we define all the states in that graph, and you know, last but not least, once we are done with all the cases, we have this always, I guess there's a typo here, underscore flip-flop at positive edge of the clock. You know, if the reset comes, we go back to the idle state. Not, we are going to go to the next state from the present state, which is, you know, the case input that we define is going to generate this this state. In the next lecture set, we're going to talk about another example, which is, a finite state machine that controls the parking lot.